Hey, I'm back. All right, this mini lecture is there's no problem in the discussion on the discussion board that deals with this particular mini lecture. However, there is a problem in the first summative exam that talks about it, and we also have in the second lab, it will also talk about this. Basically, what we're going to talk about is our graphs of distance versus time and velocity versus time, and maybe even acceleration versus time. And we're going to talk about types of motion that we see um, that we see in the book on page 31 through 33 or 35. Um, let's take a look at a very simple situation, an object at rest. Okay, so if we take a look at zero velocity, that's an object at rest. Alright, so here we have an object and it's just sitting there. It doesn't move. So the position of this object, let's say that, here's the edge of the table, or we've got it's sitting on a table, right? And the distance that this thing is away from the edge of the table, which we're going to call x, is 1 meter. Okay. Now, we get out our stopwatch at 0 seconds. The distance that this thing is from the edge is 1 meter. At 1 second, the distance it is from the edge is 1 meter. At 2 seconds, it's 1 meter. Okay, so it's going to be there. I mean, it's going to just rest. It's at rest. It's not moving. It's not going to change its position. So if we draw a graph of distance against time, all right, we come up here and this is 1 meter, 1, and here it's 2, and here we have 0 seconds, and then we go 1, 2, 3, 4, 5, etc., right? And this is in seconds. Time is in seconds, and distance here is in meters. Right? Now when we plot this, at 1 second it's going to be 1 meter away from the edge. At 2 seconds it's going to be 1 meter away from the edge. At 3 seconds, at 4 seconds, at 5 seconds, and in fact at 1.5 seconds it was 1 meter from the edge. At 2.5, at 3.5, etc. So in the distance versus time graph, we would call this distance versus time. If we get, oh boy, we're going to get a horizontal straight line for an object that's at rest. This is an object that's at rest. And if we take the slope of this line, we know that the slope from math, if you've taken math, slope is equal to the change in y all over the change in x. In this case, y is distance, so it will be change in distance all over the change in time. So for the distance versus time graph, notice that the slope of the distance versus time graph is equal to the speed or the velocity. It's equal to the speed. And we can figure out what the velocity is too from it. So what's the change when we go from this point here to this point here? What's the change in the y value? Well, it doesn't go up or down, it stays flat, right? So the change in the y value here is 0. And since y is equal to meters, it's 0 meters. Now the change in x is goes from 1 second to, we'll call it 4.2 seconds. Okay, so the change in time is 4.2 minus 1, and we'll get 0 meters all over 3.2 seconds. Now 0 divided by 3.2 is 0. So what we find here is that the velocity of that object is 0 meters per second. Okay. Now you've learned several things here. You've learned that the slope of the distance versus time graph is equal to the velocity. If we have another situation, suppose we have a situation where the object is moving, and that at time equal to 0 seconds, the object has a x value, or a distance from the edge, equal to 1 meter. Okay. At time equal 2 seconds, now let's say it's at 3 meters. At time equal to 3 seconds, let's say it's now at, no, that's not going to work. Let's say it's now at 5 meters. This is a case where each, I said 2 seconds, didn't I? So at 3 seconds, it's going to be at 4 meters. Okay. So now in this particular case, notice that it traveled 2 meters in 2 seconds, and it traveled 1 meter in 1 second. So it's traveling at a constant rate of 1 meter per second. And if we were to graph this, distance versus time, 0, and then we'll go 1, 2, 3, 4. Okay, so we go 1, 2, 3, 4. We start out at 0, 0, and at 1 meter or 1 second, this would be 1 second. There's 2 seconds. There's 3 seconds. There's 4 seconds. This is time in seconds, and this is distance in meters from the edge. Okay, we plot it up. At 0 seconds, it's sitting right there. At 2 seconds, it goes to 3. It's at 3 meters. At 4 seconds, it's at 4 meters. Now, if you notice, if I was able to draw a straight line, there's your straight line, okay? So, take a look. When the object when an object is moving at a constant speed, it will generate on the distance versus time graph a straight line. And the slope of this straight line, if it's distance versus time, will give you the speed of the object. So if we start here at 0, 1 and come over 4 seconds, and up, well, let's go over 3 seconds and up. All right, so it goes from 1 meter to 4 meters. The change in y, the change in the distance, is equal to 4 meters minus 1 meter. The change in the time goes from 0 to 3 seconds, right? So the change in the time is 3 seconds. So what we have here is that our change in distance is equal to 3 meters. And our change in time is 3 seconds. So we know that the velocity of this thing is equal to 3 meters per 3 seconds, which is equal to 1 meter per second. All right. So when you take a look at this, notice that when an object is not moving, you'll get a horizontal line. And when an object is moving at a constant speed, this is a constant speed here. So let's label it as constant speed. We'll call it constant velocity. And it's going to the right. Then we'll get a straight line, and the slope of that straight line will give you the value of the velocity. Now what I'm going to do is we're going to take a look here, and this is a pretty long one, but let's take a look at a situation where we have the distance versus time graph, and the object goes from 0, goes from right next to the edge, it goes in a straight line up, it flattens, and then it comes down steeper to the time graph. Now, over the entire trip, notice that the distance from the edge of the table has not changed. It started right at the edge and ended right at the edge. Okay? So now we can do some, there's no numbers here, so we really can't do any calculations, but what we can say is we can say that the object has a constant speed in this region here. And it's a non-zero speed. We know that in this region here, that's horizontal, so we know that it has a 0 velocity here. It's at rest. Okay, so it's just sitting there. So the object speeded up, it came to some point away from the edge, and then it slowed, and then it stopped. The object but it had a constant speed here. Here the speed was constant. Now within this region, now at the end points it had to accelerate because it had to stop. But within this region the speed is fixed. We don't know what it is, but I can say that it's fixed. Now, if you take a look at this region here, from here to here, if you compare the slope of this line with the slope of this line, which one is steeper? This line is, right? This has a steeper slope. Okay, so the speed here is greater than the speed was here. Let's label this as region A, B, and C. So region C has a greater speed than region A. Now you can also take a look at that and know, because at this point right here and this point right here, the object has been at rest. So the distance from the edge of the table is the same. But notice it doesn't take as long a time for it to get back to the edge of the table in region C. It took longer for it to get to where it ended up in region A. It just took a longer time, right? That's a longer time from here to here than it is from here to here. So we know that the speed is greater in region C than it is in region A. In addition, we know that in region A, the distance from the edge of the table increased. So in region A, the direction was away from the edge of the table. And we'll call that positive. And in region C, the direction is toward. So we'll call that negative. So what we can say about region C is it has a negative velocity, and the magnitude, the speed, is greater than the speed in region A. In region A, we know that it has a positive velocity, but the speed is not as great as in region C. So think about that. Read over these sections. In none of the regions is the acceleration anything but 0, because this is a constant speed in region A, it's at rest in region B, and it's a constant velocity in region C. So I may have said that incorrectly. In region A, the speed is constant. In region C, the speed is constant. The velocity is, away from the edge of the table in region A. We're calling that positive. The velocity is towards the edge of the table. We're calling that negative. In both cases, since the speed is not changing and the direction is not changing, the acceleration is 0. The object here is at rest, and in region B, it's at rest, and so the acceleration there is also equal to 0. So that's a lot, but if you read the section 1.4 in your book, there are some graphs in there, and hopefully this will help it make sense. If not, ask me some questions in discussion, and I'll do my best to answer them.